Welcome back, folks. Today we're going to wrap up our first unit by talking about continuity. Now, continuity is a topic that we've kind of been dealing with all the way through our first unit with limits, especially when our limits either don't exist or we found that the value of the limit is not equal to the value of the function. That's kind of a continuity issue. What we'll do today is really formalize that idea, give it some strict criteria so we can move ahead and work with it in different situations. All right, here we go. So first off, let's define continuity at a point. I'm going to say that a function f of x is continuous at a point c of its domain if the limit on f of x as x goes towards c is equal to just f of c. So if we get the same value when we evaluate the function and the limit at c, we'd say that that function is continuous at c. All right, otherwise, if that's not the case, we say that a function is discontinuous at c and that c is a point of discontinuity. All right, so let's take a look at what continuity looks like and also discontinuity. Problem 1, use the graph of f of x to identify all points of discontinuity on the interval -1 to 6. Classify each discontinuity as removable, jump, or infinite. So anytime we have a point of discontinuity, there'll be something additional we can say about it. Looking at this graph here, visually the way you can think about continuity is as you're tracing along, anytime you have to stop and lift your pencil to keep going, that's going to be a point of discontinuity. And it looks like with this graph, I'm going to have 1, 2, 3 different spots where I'd have to lift my pencil up. So our first point of discontinuity is at x equals 1. And as far as our definition goes, why is this a point of discontinuity? Well, if I evaluated f of 1, I would use the closed circle and get a 2. And that is not equal to the limit as x goes towards 1 of f of x, which in this case we'd say does not exist. So visually I had to lift my pencil, but as far as our formal definition goes, the value of the function is not the same as the limit. Now, as far as what type of discontinuity would this be, I'd say that this one is a jump discontinuity because as I'm tracing along, I have to lift my pencil and jump up to another spot and keep tracing. So we're talking about a jump discontinuity. All right, second spot I've got to lift my pencil is at x equals 3. And again, because I have this hole in the graph, so I'd have to pick my pencil up, draw a dot, and then continue. Formally, we'd say that f of 3 is equal to a 1. And that's not equal to the limit as x goes towards 3 of f of x, which when I trace this graph from both the right side and the left side, that limit's going towards 0. All right, and as far as what type of discontinuity is this, I'd say this is a removable discontinuity. Anytime you're tracing along and have just a single hole in that graph, where if I plotted one additional point, I could plug that hole, I could remove the discontinuity, we'd say that's removable. All right. And then the last point of discontinuity, last point I have to pick my pencil up, is at x equals 5. Because when I look at the value of the function, f of 5, we'd say is undefined. It looks like I have an asymptote at 5. This function doesn't tell me what to do with 5. Which is not the same thing as the limit as x goes towards 5 of f of x, which, since it's going down coming at it from the left and going up coming at it from the right, different left and right-handed limits we'd say does not exist. Okay, and don't mistake, undefined does not exist. Those are not equal to each other. Completely different issues happening here. As far as what type of discontinuity we're dealing with, that is an infinite discontinuity. Anytime you're dealing with an asymptote, we'll call that an infinite discontinuity. Okay, the limits are equal to 0 at those spots. Okay, we do have more formal definitions for these, but they're pretty straightforward. The name's pretty self-explanatory, so we won't actually get into those. Next thing we're going to do is look for points of discontinuity analytically. So in other words, by hand, no picture, no calculator to help us out. So for problem 2, it says, for each function, identify all points of discontinuity and classify each discontinuity as removable, jump, or infinite. Okay, so for a problem like this, what we're going to do is we're going to look for the removable discontinuities, any place my graph has a hole in it, and also the infinite discontinuities where my graph has an asymptote. Now, with a normal function, we're not going to have a jump discontinuity. Okay, that's only going to occur when we're dealing with piecewise defined functions. We'll look at those in a few minutes. So we're looking for is asymptotes and holes. So basically, take the same steps you would if you're going to graph this function, like back in pre-calc. First thing we'll do is we'll factor it. Looks like numerator can factor as x minus 5 times x plus 2. Over denominator, there's an x in both terms, so we can pull that out. And then graphing this, or when we look to evaluate the limits, we canceled these. But remember, they didn't go away. We said that x can't equal -2 because that would be division by 0. And I'm going to say I have everything at this point I need to identify those points of discontinuity. We're going to have a vertical asymptote at x equals 0. Okay, the zeros in the denominator that don't cancel out, that aren't also zeros in the numerator. So we could say that x equals 0 is a point of discontinuity, and it is infinite discontinuity from an asymptote. So if we find a 0 of a denominator that's not also a 0 of the numerator, we'll have an asymptote, and that will be an infinite discontinuity. Okay, the other one we have is with this term we can cancel out, the hole we're going to have in the graph. So we'll also have a discontinuity at x equals -2. Okay, the 0 of that factor. And that's going to be removable discontinuity from the hole. All right, so there's an example of what both removable and infinite discontinuities could look like in a problem like this. Part B is the same idea. Why don't you take a minute, pause the video, work through part B, and then hit play to check your answer. So we've talked about continuity at individual points. Next thing we're going to talk about is continuity over intervals of values, which leads into the idea of a continuous function. We'll say that a function is continuous on an interval if and only if it's continuous at every point on that interval. So if we have a x and a y value where the function is continuous on every single point between them, we say that is a interval that it's continuous. And then if a function is continuous on every point, a continuous function is one that's continuous on every point of its domain. So if it has no points of discontinuity, we'd say it is a continuous function. All right, so problem 3 says use the graph of f of x to identify all intervals that the function is continuous. All right, so as I look at this graph here, I'm seeing 2 points that I have to pick my pencil up to trace it. So we have 2 points of discontinuity. That means it's going to divide the graph into 1, 2, 3 continuous intervals. So the first one we'll say is everything right here. And with this picture, looks like the function continues here. Let's just assume it keeps going down to the left. So we'll say that we have a continuous interval from negative infinity to negative 1. All right, we have an additional continuous interval in the middle here. So we could just say and from negative 1 to 2. And then there's a third part from 2 on down to, since the graph keeps going, we'll assume that goes to infinity. So we could say and from 2 to infinity. Now, question students always ask is, would I place a bracket on this 2 to show that we include the 2 since we do have a solid point right here? And to answer that, I'd say no. Reason for that, if I go back to my formal definition, f of 2 is equal to 2. And the limit as x goes towards 2 of f of x, okay, does not exist. Our graph is doing different things as I come towards 2 from the left and the right side, so we say that limit doesn't exist. So at that point 2, since the function is not the same value as the limit, we'd say it's not continuous at that point. Everything above 2 it will be, okay, but not actually at that specific point. Next thing we're doing in problem 4 is look at removing discontinuities or eliminating them from the way we define functions. Part A says, for what value of k is the function f of x, this piecewise function where f of x is x squared minus 2x when x is less than or equal to 6, and 2x plus k when x is greater than or equal to 6, continuous at 6. Okay, so in other words, what value of k will make these two rules match up? Okay, we'll eliminate a jump discontinuity. And this is a very popular AP exam problem. I guarantee you're going to see one either like this or the next one where you have to find the value of k that eliminates a discontinuity. All right, here's what we'll do for that. Let's take a look at the limit of f of x from both sides as x goes towards 6. We could say the limit as x goes towards 6, okay, when it's below coming from the negative side of f of x is equal to, just substitute the 6 into this rule. That'd be a 6 squared minus 2 times 6. All right, so 36 minus 12 is going to give us a 24. Now that's actually also equal to f of 6, since that has the top rule for less than or equal to 6 as the or equal to. So that's just 24 as well. And then what we need to do here is make this limit as x goes towards 6 from the right match up. So the limit as x goes towards 6 from the right when x is greater than 6 of f of x is going to be equal to 2 times 6 plus the k. In other words, 12 plus k. So essentially what we need to do here is find the k value that makes this limit equal to the 24 coming from both the left side of the limit and the value of the function. Okay, so kind of making an equation out of the two of these, we'd have that 24 is equal to 12 plus k. Simple algebra, subtract 12 on both sides, and we end up with k is equal to 12. All right, so if I substituted in 12 for this k, we would have a continuous function. Let's take a look at another way this type of problem can work out. Once again, for what value of k is the function g of x continuous at x equals negative 3? Once again, we have a piecewise defined function, and this time we're going to define it as this rational function here for every x value except for negative 3. And at negative 3, we're going to assign it the value of k. So let's take a look at how we can make this continuous. Okay, first thing, I'm thinking with this rational expression, there's some kind of issue when we plug in negative 3. Let's take a look. If I go negative 3 squared plus 5 times negative 3 plus 6 over negative 3 plus 3, right off the bat, I see I'm going to have a 0 in my denominator. And I'll also have a 0 up top, so 9 minus 15 plus 6 will give me 0 as well. Okay, so this function is undefined at x equals negative 3, or at least this rational expression is. So that's why I need this k for when x is equal to negative 3 to make this function defined. Now, we could pick the k to be anything we want to define it. But if we want to make this function continuous, we need that value for k to match up with the limit of this function. So let's find that limit. Like we see here, we have a indeterminate form when we plug in just the negative 3. So what we'll look to do is factor this guy. So we're looking at the limit as x goes towards negative 3 of this expression factored. I can write that as x plus 3 times x plus 2 over x plus 3. And since there's a common factor on top and bottom, we can cancel that out. And we can just rewrite this as the limit as x goes towards negative 3 of x plus 2, which we can do direct substitution on. Negative 3 plus 2 is just equal to a negative 1. All right, so if this is how we're defining our g of x for all values except for negative 3, the limit as x goes to negative 3 of g of x is negative 1. That means for this k value, we have to say k is equal to negative 1. That way, by definition, g of negative 1, g of negative 3, it's getting ahead of myself, is equal to negative 1, and I have my limit matching the function definition at that value. Okay, so therefore we're continuous. Last thing we're going to take a look at is something called the intermediate value theorem. That says this: if a function f of x is continuous on a closed interval, a to b, so if we have some function f of x and it's continuous, it's smooth, there's no holes in it from x equals a to x equals b, and k is a number such that f of a is less than or equal to k, which is less than or equal to f of b, so k is between f of a and f of b, then there exists the number c in a to b such that f of c equals k. All right, so again, if f of x is continuous and k is between f of a and f of b, that means there has to be some value between a and b, okay, that gives us that value here. Okay, that's my theorem. We're not going to go through a formal proof of it. It's kind of common sense. Basically what it's saying that is if I have a point here and here on a continuous function, for me to connect these dots crossing K, I'm going to also have to cross that C. Okay, that's whether it's a nice smooth kind of connection there, or we could have some function that goes wildly all over the place. Again, at some point, we're going to hit that value C, okay, that intermediate value. Let's take a look at how the intermediate value theorem could show up for us on an AP exam. Here's an example of something you could see on the multiple choice portion of the test. Problem 5 says, selected values of a continuous function f are given in the table below. So we have values for x and f of x. And the reason we're able to apply our intermediate value theorem here is because it says it's continuous. So in other words, if I plotted these points, we could think about connecting the dots. Problem A says, what's the minimum number of times the function takes on the value f of x equals 2? All right, well, let's take a look. We want to count basically how many times our function passes that 2. All right, from 1 to -5, we may somewhere between 0 and 1 go past 2, but based on the data we have, we can't say that for sure. Okay, same thing with -4, -5 to -4, doesn't necessarily have to pass it. But if my function's values go between -4 and 4, that's going to be one time that this graph is going to have to pass f of x equals 2. So know that between 2 and 3, by the intermediate value theorem, there's at least one value that gives us that f of x equals 2. Same thing as I go here from 4 to -10, we know we're going to have to pass 2 at least once, so that'd be one more at least x value between 3 and 4 where we pass 2. Okay, so how many times would f of x equal 2? Well, that would be 2 total times here. Let's take a look at part B, same idea. What's the minimum number of times the function takes on the value f of x equals -7? Well, from 4 to -10, we have to pass -7. So that'd be one time. -10 to -15 could go back, but it doesn't necessarily have to. Same thing up here. Guess that's why we'd have the one time it has to cross, okay, based on what the results of that intermediate value theorem. Let's take a look at another way that the intermediate value theorem could show up on the AP exam. Okay, and this will be a popular free response question part. I guarantee AP exam time, you're either going to see one example like this using either the intermediate value theorem or the mean value theorem. All right, so let the continuous function q of x be defined by q of x equals sine of x plus cosine of x. Must there exist a value of c on the closed interval 0 to pi over 4 for which q of c equals 1.02? Justify your answer. All right, so in other words, is there a value between 0 and pi over 4 that makes q equal to 1.2? Here's how we can do this. Since the function is continuous, I can apply my mean value theorem. I can take a look at the first value in my interval, 0, and figure out q of 0. Q of 0 is going to be equal to sine of 0 plus cosine of 0. Which, if I think back to my graphs of sine and cosine, sine was my graph that started off at 0, 0. So I know the sine of 0 is just 0. Okay, plus I know the cosine of 0 is a 1. 0 plus 1 is just equal to 1. Okay, so that'd be my value for the first part of that interval. We'll also look at q of pi over 4, which would be equal to sine of pi over 4 plus cosine of pi over 4. Now, as far as what that's equal to, we got a little trig to do. Let's make a little side note here. All right, pi over 4 radians is the same thing as 45 degrees. All right, we know that pi radians is 180 degrees, so 180 essentially divided by 4 would give us 45. And the way that we can evaluate the sine or cosine of 45 degrees is just by going to our special right triangles. For that, we can utilize our 45, 45, 90 right triangle. All right, it had side lengths of 1, 1, and root 2. And then to find the actual sines and cosines, what we'll do is we'll label this triangle based on our trig definitions. Okay, based on our so, ka, toa. So the two 45s are the same. I'm just going to pick this one to use. If I do that, that means the side across from it is the opposite side. Side next to it would be the adjacent side. And across from the right angle is the hypotenuse. Okay, we defined sine as the opposite over the hypotenuse. Opposite's 1, hypotenuse is 2. So that'll just be equal to a 1 over root 2. And then same thing for cosine. Cosine is the adjacent over the hypotenuse. Adjacent side's 1, hypotenuse is root 2, so that'd be plus another 1 over root 2. All right, adding those together, we do have a common denominator, so we can just go 1 plus 1 is 2 on top over root 2. And we could leave it like this if it's the no calculator part of the exam. This is kind of all the further we could take it. If this was on the calculator part, we could approximate that. 2 divided by square root 2 is approximately, we could say, 1.414. And I guess the other thing is I know since 2 is greater than root 2, I know this is going to be more than 1. Okay, it should be more than 1.02. All right, so we showed here is that q of 0 is a 1. Q of pi over 4 is a 1.414. Since this function is continuous, yes, we should have a value between 0 and pi over 4 where it hits that 1.02. So as far as the justification goes, we'll say yes and explain how we're able to apply the intermediate value theorem. Since q of x is continuous, and I know that q of 0 is equal to 1, which is less than or equal to 1.02, which is less than or equal to 1.414, which is equal to q of pi over 4. Okay, so since we have the criteria for the intermediate value theorem, we can apply it. Okay, so since it's continuous and that value fits within the interval, we can say, comma, by the intermediate value theorem, and it's a name, I suppose I should capitalize it. Sounds better. By the intermediate value theorem, there exists a c on the interval 0 less than or equal to c less than or equal to pi over 4 such that q of c equals 1.02. All right, that's going to be the standard way that you justify results based on the intermediate value theorem. When it asks this question on the AP exam, typically the yes or no part is going to be at 1 point, and then just repeating what you see here, since q of x is continuous, you need that, and the value we're looking for falls within our interval. By the intermediate value theorem, there exists a c on that interval such that we get the result we're looking for. Okay, that justification would be another point. Okay, 2 free response points for something that's going to work out exactly like this when you get the AP exam. Okay, I think those should be some easy points for you. For our last example, we're going to take a look at one where the intermediate value theorem is inconclusive. It doesn't tell us anything new. For part B, the function f of x equals tan x is continuous on its domain. Okay, so tangent of x is not a continuous function. There's asymptotes in it. But if we look at just its domain, it would be continuous on those values. We want to know, must there exist a value of c on the closed interval negative pi over 3 to pi over 3 for which f of c equals 3? Justify your answer. Okay, we'll start once again by looking at the endpoints plugged into our function. So tan of negative pi over 3 and tangent of pi over 3. Let's start with a positive case first, just to do the simpler one. Okay, for tangent of pi over 3, to do that, let's do some trig scratch work here again. Pi over 3 radians is going to be equal to 180 divided by 3, or 60 degrees. All right, to evaluate that, we can use our 30, 60, 90 right triangle. 30, 60, 90, with side lengths 1 across from the 30, root 3 across from the 60, and 2 as the hypotenuse. And again, we're talking SOH, CA, tangent is opposite over adjacent. So if I take my 60 here, my opposite side would be that root 3, and the adjacent side would be the 1. So in other words, tangent of pi over 3 would just be a root 3 over 1, or in other words, just root 3. All right, so a little trig review there. Now, this type of problem doesn't have to involve trig, but I included it in the notes just to get us some more trig practice. So we've got the upper bound. Let's take a look at the lower bound of our interval. Tangent of negative pi over 3. Now, negative pi over 3 is just equal to negative 60 degrees. And how do we evaluate a negative angle? Well, for that, we're going to have to go to angles in standard position. And positive angles, like a positive 60, would open up on our coordinate system. Negative angles, though, are going to open down. So let's put our negative 60 degrees here. Now let's apply that same special right triangle in this case. So we've got our 60, 30, 1 across from the 30, root 3 across from the 60, and 2 is the hypotenuse. Now the only difference here is since my root 3 is going in the negative y direction, I'm going to say that's a negative value. 1's still moving in the positive x direction, so that's positive. And the hypotenuse, we're going to say, is always positive. Okay, it's a distance, it's not an x or y direction. So again, we'll look at the opposite over the adjacent of our 60. Opposite's negative root 3, adjacent's 1. So that would evaluate just to a 1 over negative root 3. Whoops, I just did that backwards. A negative root 3 over 1, there we go, opposite over adjacent, which is just a negative root 3. All right, so here's the issue with this one then. F of negative pi over 3 is negative root 3. F of pi over 3 is root 3. We want to try to figure out if the function's ever equal to 3. Okay, that's outside this interval. So we can say that since since f of pi over 3 equals root 3 which is less than 3, we cannot apply the intermediate value theorem. All right, so since we're outside of those bounds, we can't apply the intermediate value theorem. There's other ways we could figure out, okay, if there's anything between the two of these, but since our intermediate value theorem's criteria aren't met, we can't use it to apply to that. Okay, it still could be true. Now, if you think of the graph of the tangent function, it's not, but we can't conclude that based on the intermediate value theorem. All right, so that's it for lesson 1.5, and that's it for unit 1 actually as well. Okay, start going to town on the homework, get practice, make sure you're asking questions if you have them, and we'll see you next time. Okay, no jump continuity, point of discontinuity happening.